For decades, the scientific consensus regarding the lifespan of Earth's terrestrial biosphere has been absolute. We have exactly 1 billion years of habitability left. The accepted kill mechanism in this model is global carbon dioxide starvation, driven by the steadily increasing brightness of our aging sun. But newly published biogeochemical data upends that timeline. By feeding updated planetary weathering measurements into a global mean climate model, researchers have effectively doubled the lifespan of Earth's complex biosphere to 1.86 billion years. The terrestrial biosphere will not die from carbon starvation. It will die from thermal overheating. To understand how the timeline shifted so drastically, we must dismantle the old model's parameters and reconstruct Earth's geological endgame using current data. Recalibrating the date of Earth's demise changes our planet's timeline and the statistical probability of finding complex, intelligent life elsewhere. Over deep geological time, Earth's climate is governed by a strict physical relationship. As the sun ages, it fuses hydrogen into helium, causing its core to contract and its solar luminosity to increase, driving up Earth's surface temperature. To prevent the oceans from boiling off, Earth relies on a long-term geological thermostat known as the carbonate-silicate weathering cycle. As the sun brightens and temperatures rise, rain falls more heavily on silicate rocks. This chemical weathering process accelerates, aggressively dissolving atmospheric CO2 into runoff that washes into the oceans, eventually getting buried on the seafloor to keep the planet cool. The legacy model assumed a fatal consequence of this thermostat. To counteract a brighter sun, the weathering cycle would eventually pull so much CO2 out of the atmosphere that levels would drop below the minimum threshold required for vascular plant survival. This conclusion was driven by two specific parameters. Silicate weathering was modeled as highly temperature-dependent, meaning it reacts strongly to warming, and weakly CO2-dependent. This specific kinetic ratio locks the Earth into a one-way trajectory. Solar luminosity climbs, temperature follows, weathering spikes, and CO2 is rapidly forced down to zero. The 1 billion-year starvation model relies entirely on those specific geochemical equations holding true. Recent proxy data reveals those equations are incomplete. Before calculating the new atmospheric trajectory, we have to correct the biological boundaries of the model, starting with the thermal limits of plant life. Legacy simulations assumed that 323 Kelvin, or 50 degrees Celsius, was the absolute thermal ceiling for photosynthesis. Above that, the enzymes required for carbon fixation were thought to degrade. Field observations of desert extremophiles disprove this ceiling. The desert shrub Tidostromia oblongifolia operates at its peak photosynthetic rate exactly at that mark, meaning it is an optimal temperature for some species, not a lethal limit. The actual upper limit is defined by species like Dicanthalium lanuginosum, a grass that uses a symbiotic root fungus to survive prolonged exposure to geothermal heat. Based on these thermotolerant species, the new thermal death threshold for the complex biosphere sits at 338 Kelvin, or 65 degrees Celsius. We also need to correct the CO2 starvation limit at the opposite end of the spectrum, looking specifically at the physiology of C4 plants. C4 plants, like modern grasses and corn, utilize a highly efficient carbon-concentrating mechanism. They physically pump CO2 into specialized bundle sheath cells, saturating their photosynthetic enzymes, even when atmospheric carbon is incredibly scarce. Because of this internal concentration, the absolute minimum CO2 compensation point for C4 plants to survive is a mere 2.9 parts per million. By correcting these two physiological boundaries, the terrestrial biosphere now has a much larger operational survival envelope than legacy models permitted. With the biological limits expanded, we apply the geological correction to the two kinetic variables governing silicate weathering. Modern geological proxy data indicates that the legacy parameters were inverted. Silicate weathering is actually weakly temperature-dependent and strongly CO2-dependent. This chart maps out the phase space of our planet's future climate. The x-axis tracks atmospheric CO2 concentration, and the y-axis charts global mean surface temperature. Applying our corrected biological boundaries, we set the absolute CO2 starvation limit at 2.9 parts per million, and the thermal death limit at the horizontal line of 338 Kelvin. Following the legacy model's parameters, we trace this lower path. Driven by strong temperature dependence, it crashes directly into the vertical starvation wall long before surface temperatures become critical. Now we trace the updated trajectories based on the modern weekly temperature-dependent data. These upper curves begin to approach the CO2 starvation line, but the kinetic mechanics force them to behave differently. A powerful biological feedback loop engages. As less efficient C3 plants begin to die off from low carbon, total plant productivity drops. This reduces the amount of CO2 plants pump into the soil, which in turn heavily decelerates the silicate weathering rate. Because weathering is strongly CO2 dependent in this model, this deceleration causes the atmospheric carbon drop to halt entirely and then briefly reverse. This buffer prevents CO2 starvation. The atmosphere holds on to enough carbon for C4 plants to survive, while the planet continues to warm under the increasingly luminous sun. The trajectory veers upward through the map until it ultimately intersects the 338 Kelvin limit. The interplay between climate, plant productivity, and weathering steers Earth physically away from carbon starvation. The terrestrial biosphere will survive for nearly another billion years until it simply overheats. Extending the future lifespan of the biosphere by 860 million years forces a recalculation of a major astrobiological theory. Researchers use a statistical framework called the Carter model to estimate the improbability of intelligent life evolving in the universe. The core premise is based on time. If the evolution of intelligent observers requires a series of highly improbable evolutionary transitions, called hard steps, and each step takes an immense amount of time, then intelligence should only ever emerge at the very end of a planet's habitable window. The formula estimates the hard steps, n, by dividing the time intelligence took to evolve by the remaining habitable time. Using legacy data, 4.4 billion years elapsed, 1 billion left. That yields roughly 5 hard steps. This 5-step process implies complex life is a statistical anomaly, clearing near impossible hurdles to exist. But if we input the updated 1.86 billion year future lifespan into the equation, the required number of hard steps drops to approximately 2.4. Under this calculation, human intelligence did not emerge at the last possible second. It emerged relatively early inside a massive 6.5 billion year total habitable window. Because the biosphere has a much longer future lifespan, the mathematics show that the evolution of intelligence required fewer highly improbable transitions than previously believed. We can apply this specific timing to the very first evolutionary hard step, the origin of life itself. In a 5-step model, the fact that simple life appeared almost immediately after early Earth's oceans formed was a statistical anomaly. It happened far too fast for a supposedly improbable event. In a 2-step model, that rapid timeline fits the math. The quick emergence of life on Earth is exactly what the statistics expect to see. We can project these updated weathering parameterizations and thermal thresholds outward to exoplanets orbiting distant stars. The inner edge of the habitable zone for complex life on these planets is dictated by thermal biological limits, not past carbon starvation models. By correcting the geological equations that govern our own biosphere's destruction, we increase the statistical probability of finding complex, intelligent life elsewhere in the cosmos.